Now, when you think about it, Newton's third law says that if the south pole is being pushed that way, the wire is being pushed the other way, equal and opposite. Are we set up? Okay. What are the chances that all of this is going to work? This is ambitious. Ambitious. I'm excited for today's lecture. This is, without a doubt, my favorite lecture of the 106 class. Just like the Newton's third law is my favorite topic of physics 105. Lenz's law is the second most beautiful physical law of the universe. And I've got to believe that our Heavenly Father is proud of this one. Okay. Hey, Clark. Time you showed us, Stephen. Stephen, while you're standing, give us a prayer.
Our dear Congress of coming Father, we both Francis has as well.
Amen. Thank you, Stephen. Okay. The idea that we're going to try to drive home today is a little subtle. People struggle with it a little bit at first, but I would encourage you to strap in and stay engaged, because if you decide to check out, and maybe I'll understand this later, you're going to miss all the practice that we're going to do. We're going to develop the idea, and then we're going to practice. But if you're not with me while we're developing the idea, the practice isn't going to make any sense, and it's not going to help you get ready for an exam or for the homework. So let's see what we remember. You remember last day we talked about making a metal detector, and that was basically just a magnet detector, which was just a coil. In this case, we put the wire around the door, and whenever a magnet went through, we induced, I can't see the battery that's causing it, we induced this current around the coil. And then to make it a metal detector, we just had to magnetize the metal with another coil, kind of like making an electromagnet, okay? Now, we found with Faraday, he actually found it before we did, that it was magnetic flux that was important. And magnetic flux was the number of field lines that went through the loop. Now, we're going to treat magnetic flux as a vector. In principle, it's a scalar quantity, but if you treat it as a scalar, you're going to end up with another right-hand rule and a bunch of minus signs. And I think we can all agree that's the last thing we need. So we're going to treat that as a vector that has the same direction that the B field is going through the loop. Now, it becomes useful today to distinguish between two different flavors of field line, of flux. First of all, we'll talk about external flux, and that's due to everything that's not the coil, okay? So in this case, it would be the field lines due to this bar magnet, okay? And then there's induced flux, and that is as soon as I get the current going around the loop, well, it becomes a little electromagnet. It's got its own magnetic field lines. And Lenz's law connects those two, the induced flux to the external flux. But not really the external flux, the change in external flux. We'll get there. You remember this was Faraday's law in a nutshell. And that EMF there is the invisible battery. And that's induced, that's pushing that induced current. Now, if this is how quickly we change the number of external field lines through a single loop, and then we multiply by how many loops we have, we get that EMF. Now, the piece we haven't talked about yet, and that's the topic of today's lecture, is that minus sign, okay? And it has its own name. That's Lenz's law. That's Lenz's law. And what it means, I hope you'll come to realize, is fight, okay? Fight, okay? Lenz's law, the minus sign. The induced magnetic flux through the loop always opposes, always fights the change in the external magnetic flux. Tell your neighbor what the most important word in that sentence is. There's one word that's more important than all the others put together. What is it?
Change. Yeah. That's awesome. Or always.
Okay. I hope you told your neighbor that the word is change. It's the change. Oh, we got a winner. Okay. Now, I'm going to do a demo here that I'm really excited about, because this demo someday I think is going to make me filthy rich. What I have here is this is a brass pipe. I prefer to have a copper pipe, but this is what we've got. And what I've got is a magnet and something that's not a magnet. It's just steel, okay? And you see that this doesn't stick. That doesn't stick either. I need some iron here. Oh, there we go. So this is clearly a magnet, and this clearly is not. Now, we're going to have a little race, okay? And I'm going to put this, who's ready to catch it? You're ready to catch it, okay? We're gonna time this as it falls through this tube. Ready, set, go. Whoa, that was less than a second, don't you think? Okay. Ready, set, go. Pretty quick. Okay, now, remembering that magnets don't stick to brass, they're non-magnetic. How long do you think it's going to take the magnet to go through? Is it going to be the same, longer, or shorter? Tell your neighbor real quick. Okay. Now, the cute little vent there. That's exciting. So it's non-magnetic. So it's going to take exactly the same time to get through. Watch. Ready, set, go. One, about the same time, less than a second. Okay. Is that what you saw? Let's try it again. 1,000. Got stuck in there. Okay, let's try with a tube that's not bent. I've got here aluminum tube, and again, aluminum's non-magnetic. Where did our steel piece go? Right here. So if we have our catcher, ready, set, go. So less than a second. Now, this is a magnet, and ready, set. and it's out. That was longer, I'd say, okay? Now, ideally, what we would love to have, and Clark and I are gonna be on the lookout for such a thing. If you run across one, give us a holler. A big, thick pipe of copper. And that's what I've got in this video. We're going to watch as a magnet is dropped down the barrel of this copper pipe. So. Isn't that the coolest thing? I mean, it wasn't stuck, it was just floating down there slowly like that. Well, let's talk about why that is. What's going on there? This is a depiction of that tube of copper. And let's suppose that we drop that permanent magnet down the hole with the North Pole facing down. That's what the red means in my slides, is the North Pole, okay? Now, with that falling magnet, I have to remember what Faraday taught me. And that is, when I bring a North Pole near a copper loop, I set up a current, do I not? An induced current. And that pipe is made out of copper. And that bar magnet is approaching the bottom part of that copper pipe, just like I'm approaching this copper ring with this North Pole. That's going to set up an induced current, and that induced current has to be, we just saw, in a direction to fight the motion. And that's what we learned in that tutorial this week. And that's going to be the case if the electromagnet that's set up at the bottom of the pipe has a North Pole up to fight that North Pole coming down. Well, that's only half of it, because not only is the North Pole approaching the bottom of the pipe, the South Pole is leaving the top of the pipe. And that's copper. That's a copper loop. And so that's going to set up an induced current up there. And again, it has to fight the motion. Okay, in this case, it would be with a North Pole down, so that I've got a North Pole against a South Pole saying, don't leave me, don't leave me. Okay, so this current up here is pulling on the South Pole up. This current down here is pushing on the North Pole up. Both of them are fighting the motion. Now, why do the currents have to be that way? They have to be that way because of one of the most important principles that we learned in Physics 105, and that is conservation of energy. That current that shows up is energy. It's got to be paid for, okay? And the way it's paid for is from the gravitational potential energy bucket. If I would just drop that magnet without the copper pipe, I would lose gravitational energy, but I would gain kinetic energy. If I lost 10 joules of gravitational energy, I would gain 10 joules of kinetic energy. But here we see I lose the potential energy. It's getting closer to the floor, but it's not speeding up. Once it gets going at that slow rate, it's not speeding up. So that energy is going into making the current. Now, think about what the world would be like if it went the other way. If it went the other way, I could take that great big copper pipe that you saw in the movie, throw it on my shoulder, put a little magnet in the back and give it a tap, and what? What's going to happen? Yeah, it's going to fire out like a bazooka. You know, if those induced currents were the other way, they would speed the magnet up. That doesn't make sense based on what we know about energy. See if your neighbor's on the bus.
Wait, the current going down.
Okay. I said that I hoped that this demo would make me filthy rich, whereas now I'm just filthy. How am I gonna do that? Well, I hope someday to make a great big huge copper tube, not like what we saw in the movie, but as big around as this room and 10 stories tall. And then I'm gonna get a suit and put magnets all over it. And then what? No, I'm not gonna jump in. I'm gonna charge each of you $50 to put on the suit and jump in and just float and flip and have fun all the way down. And it's gonna be worth the $50 because every morning I'm gonna have to pay my brother Kenny to put on the suit and jump in the first time. Why? Because if some terrorist came in the middle of the night and cut a slice down the side of that tube, what happens to Kenny? Yeah, falls like a rock. But Kenny would do it. For money, Kenny would do that. He's a good kid. Okay. Now, fun fact, this won't be on the exam. This demo was first done in India. And then a colleague of mine visiting India brought it back to the States, Jerry Wheeler. And Jerry and Larry Kirkpatrick were in charge of a big national conference, AAPT, that was held in Bozeman, Montana, about 37 years ago. And Jerry showed this demo to this huge gathering of geeks, of physicists. And before the end of the day, the local feed store, Big R, had completely sold out of their cow magnets. Back then, we didn't have neodymium magnets. The best we could do were cow magnets. You were city folk, I understand. But cow magnets, you get the cow to swallow it, and it kind of gathers all of the spare metal that they've put in their belly, and it protects the cow. So anyway, the people at Big R were just amazed that they had sold so many magnets, and the people that came to buy them were just weird physicists. Okay. Now, moving right along, we're going to use this idea to develop Lenz's law. And here's how we're going to do it. I have here a conducting ring. I'm going to put on the table there. And I'm going to do two little experiments. The first one is I'm going to take a North Pole and move it down towards that ring. That's experiment one. Experiment two is I'm going to take that North Pole and pull it away from the ring. Okay, so let's look at those two experiments. The first one, I bring that North Pole down. And the question is, what direction must the induced magnet be in order to fight back, in order to fight that North Pole coming down? What do I want facing that North Pole if I'm going to fight the motion? Another North Pole, yeah. Now, folks, your right hand, okay, you've got a curved part of that right hand. What direction does the induced current have to flow in this conducting loop to make that North Pole face up? Is it going to be clockwise or counterclockwise? Shout it out. Wonderful, a mighty shout went up in the land, okay? It's going to be counterclockwise. Now, I want you to think about two different kinds of flux, field lines, through that loop, okay? The external and the induced, okay? The external flux is due to the bar magnet, anything that's not the loop. And we know that the field lines come out of a north and then they spread out. So not many of those field lines make it through that loop, but they go through the loop pointing towards the floor. Are we good with that? Now, the induced flux, we said, was up. Notice that that's opposite. That's not important at all. That's just a coincidence. Okay? Now, as that North Pole gets closer and closer, this external flux gets bigger and bigger. And again, that's because those field lines from the bar magnet spread out. When I get closer, more of them are going to make it through the loop. Are we on board? Okay. Now, the second experiment. I take that North Pole and I pull it away. What kind of bar magnet does this have to become to fight that motion? What do I want facing that North Pole now? Yeah, South Pole. Yeah, to pull back, I need a South Pole against the North Pole saying, come back, okay? What direction does my induced current have to flow in that loop to make this kind of electromagnet? Yeah, it's got to go clockwise this time. Oops, got to go clockwise. So let's look at the two flavors of flux now. I've got external flux that is down and induced flux that is down. They're in the same direction. And that's not important at all. Okay? Don't even care about that. Now, as that North Pole gets further and further away, that external flux gets smaller and smaller. Okay? Now, we are this close, people. We are this close to putting it all together. Everyone, look to your right, look to your left, and see if your neighbor is ready for it. Okay? If not, just slap them silly.
I guess so.
Here is the $50,000 idea. When I'm bringing the North Pole down, I started with external flux that was small because the magnet was far away. And then it got big. What I care about is not the external flux, but the change in external flux. What do I have to add to this earlier vector to get this later vector? What do I have to add to a short vector down to turn it into a long vector down? I've got to add something down. There's the plus sign right there. That's how we add vectors. The short one plus the change gives me what I ended up with. Now, remember, the induced flux in this case was up, opposite that change. Now, if I look at the second experiment, I started with a lot of external flux because the North Pole was close to begin with. And when it got farther away, I didn't have so much flux. What I care about is the change. What do I have to add to this big vector down to get a small vector down? I have to add something up. There's the plus sign right there. Okay, there's the plus sign. And again, the induced flux was down in this case, opposite the change. That you can take to the bank. It is always, 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 the induced flux is always opposite the direction of the change in external flux. Conducting loops hate change. They're like Republicans, okay? They hate change, okay? Okay? And so they fight the change by setting up their own field lines, okay? See if your neighbor understands Lenz's law now. Okay. Questions? Okay, let's practice. We're just going to practice until this is part of us. This is part of our toolbox. If I bring a south pole towards this solenoid, now what is that solenoid there? Suppose that I took a toilet paper roll, the tube in the middle of the toilet paper, and I wrapped a wire around it and around it, around it, around it. And then I took the ends of the wire and I connected them together. I just soldered them together like that. Now, when we induce current in this coil, the current's going to go around either one way or the other. The induced current's either going to go up the front and down the back, up the front and down the back, up the front and down the back. In that case, the current would go through this wire to the left. The other option is the induced current could go up the back and down the front, up the back and down the front, up the back and down the front, and then the current would go to the right in this wire. So your job is to figure out with your neighbor, which way does the current flow right here, the induced current, because I'm bringing that south pole closer, okay? And your choices with your clicker are left, right, or I'm so confused. Oh.
Okay, so the motion.
Okay, I'll get you started.
But the current's gonna go this way.
Okay, now you can click.
Well, it's gonna come back.
We're almost there, son. So.
Like my brain's saying like.
Okay. Get your vote in, people. Last call. Okay. Whoa, okay, right. Well, let's see if you're right. Some of us aren't, okay? Let's first of all, use the approach that this induced current will always, when there's motion, it will fight that motion. It will fight that motion, okay? So if I want to fight the motion of this south pole coming closer to that coil, this has to turn into a bar magnet with what kind of pole here on the left? A south, yes, okay? And so now we just have to figure out what kind of induced current is going to give me a south pole over there. But what I really ask myself is what kind of induced current is going to give me a north pole on the right? Because that's my thumb, okay? If I point my thumb in the direction of the north pole, my curved part of the hand is going to tell me which way the induced current goes. It's going to go up the back and down the front, up the back, down the front, and down the front means to the right. And so it's going to go to the right. See if your neighbor got that correct. See if your neighbor is on the button.
That's a lot of things, right?
Oh, it's there.
It's gonna go this way. Oh. Oh, that's. Well. Yeah, but.
Get the crescendo. I love it. I couldn't help this. Okay. Folks, what you learned on the last page of the tutorial is that while this approach that we just used, fight the motion, is easy, it doesn't always work because we've seen some cases where there wasn't relative motion. And so in those cases, what you have to rely on is Lenz's law. So let's solve this again, but this time we're going to do it with Lenz's law. First of all, I asked myself, which kind of flux do I care about when I'm looking for the change? Is it the flux due to the bar magnet or the flux due to the induced current in the coil? What are we looking for the change of?
External.
Yeah, the external flux, the external flux. And so I have to keep straight in my mind what I mean by external, what I mean by induced. Okay, external is everything that's not the coil. In this case, the bar magnet. Okay, now the magnetic field due to this bar magnet over here, I know what it is everywhere. It comes out of the north, it swings around, it comes into the south. But I don't care what it is everywhere. I care what it is right there in the middle of that coil, okay? And right there, it's going to be towards the south. Now, as I bring that south pole closer, more of those field lines are going to be passing through this solenoid. And so the flux, the number of field lines, gets bigger. Now, what I care about is the change. What do I have to add to this small vector to the left to get a large vector to the left? I got to add that change right there. There's a plus sign right there. Okay. Now, the induced flux fights that change. And so it has to be the other way. Now, folks, there is a mistake in this slide that I put there on purpose. Okay. Can anyone see what it is? It's subtle. I made the induced flux just as big as the change in external flux. And if that were the case, the external flux through the loop wouldn't be able to change. It wouldn't be able to ever change. So that induced flux fights the change, but it never wins. Okay? It never wins. It's like Massachusetts Republicans, okay? They fight the change, but they never win. And that worked until my good friend Mitt Romney became governor of Massachusetts. And he's a wonderful, wonderful human being. When he was bishop, I was his executive secretary, and my dear wife was his primary president. And my wife, bless her heart, she invited the Romneys to our little student apartment, our little tiny student apartment for dinner. And when I found out, I said, "You what? The Romneys?" And sure enough, they showed up and were just as gracious as could be. And they, you could touch both sides of our front room while sitting on the couch. So anyway, wonderful people. Okay, that's not going to be on the test. Okay, now, once I have the induced flux is to the right, I do the right-hand rule number 3 again to get the current that's causing that flux going through that wire to the right. Okay, let's try another one. What if I have a north pole and I'm taking it away from the coil? Tell your neighbor which way the current's going to flow right there. Is it going to be right, left, or I still don't know?
No, left. South is gonna have to face the north. If the market is right, then the south has to be towards the north. It would be, oh, okay. I was thinking that it was coming this way, but it's. No, I. Oh. Oh, no. Oh, I did, and then I was like.
That is so inspiring just to see you all doing this. You know, when you get to that next exam in the testing center, they're going to really worry about you. Okay, go give them a glass of water. Freaking out. Okay, let's do it together. When the North Pole is close, because those field lines spread out, I still have a lot of those field lines that make it through the coil. But when it gets further away, not so many, okay? What I care about is the change what do I have to add to this long vector to turn it into a short vector? I have to add something in the opposite direction. There's the plus sign again, okay? Now the induced flux has to fight that change. If the change was to the right, the induced has to be to the left. And that means my north pole will be to the left. That means the induced current goes up the front, down the back, up the front, down the back, up the front, down the back, and to the left here. Yes.
Can you put the change arrows again?
Uh-huh.
When you said there's the plus sign again, what do you, like, there's big
When you add vectors, you stack them head to tail. Okay, I take this vector that I started with, I add this change, and what I get when I add vectors, I go from the first starting place to the last ending place as the crow flies. And so if I had, after this class, if you went over to the Marriott Center for the devotional with the coach, and then you went to the Cannon Center to get some lunch, the total of those two vectors would be from the very first starting place to the very last ending place. And there's the plus sign. If that was A and this was B, this would be A plus B.
So you're referring to the purple as a plus sign as opposed to the direction?
No, I'm referring to this, where I've got this arrowhead and this tail of the vector. By stacking them head to tail, that's the plus sign. Here, the plus sign was right here where I didn't have this vector over here. I moved it so that its tail was at the end. Am I not understanding the question?
My question was that on the exact same, the previous problems, the purple arrow was facing the wrong way, but we still referred to it as there's a positive. So does the direction of the arrow, the change?
Oh,
matter
oh. The plus sign, when we're adding vectors, means something completely different than the plus sign when you're adding numbers. 4 plus 3 in numbers is 7, but 4 plus 3, when you're dealing with vectors, if I have them in the same direction, that's going to be 7. If I have them in opposite directions, that's going to be 1. And if I have them perpendicular to each other, that's going to be 5. Depending on the angle, it could be anything between 7 and 1. Clark?
So my confusion that I think I'm hearing there is that you're taking a change, which is actually a subtraction vector, so you're adding the opposite.
Well, yes.
I don't know if they're seeing that.
So if my change, let's say, let's do velocity. My change is equal to V final minus V initial. If I add V initial to both sides, then the change can be thought of as the difference between the two vectors, but it can also be thought of as what I have to add to what I started the morning with to get what I ended the day with. Okay, and we always feel more comfortable with adding vectors than subtracting, I find. Does that make sense? Okay. Now, where was I? You remember that if I had two coils next to each other, this one we called the secondary coil, and this one we called the primary coil, and this was it was attached to a battery when I closed the switch. And what we found last day was that right as I closed the switch, I got an induced current in this secondary coil, just for a minute. Wasn't a minute, it was just for a blink of the eye, and then it went away. and it stayed away until I opened the switch. Well, let's look at that for a moment, okay? What is the current direction in this right loop, in that wire right there, right when I close the switch? Use your clicker to answer that question. Now you can click.
Because on the left, it's gonna go right, that's right. But I think as it supports it, it's maybe a little closer.
I apologize. I may have assumed that all of you had 105 with me and are used to my terminology for things. That may not be the case. Okay. Last call. Let's see how we did. Oh, yeah, it's either right or left. Well, that's certainly true. Okay, let's do it together. When the switch is open, what field do I get over here due to that solenoid over there? Nothing. It's not a magnet. The switch is open. There's no current over there. It's just a bunch of copper. Okay. And so I get nothing. But when I close the switch, it's not nothing. Okay. Now, by closing that switch, this is the positive terminal of the battery. Conventional current's going to go out of the positive terminal of the battery, up the front, down the back, and that's going to make this the north pole and this the south pole. Now, that means the magnetic field due to this electromagnet is going to come out of the north and into the south, but I don't care about it everywhere. I care about it over here. And over here, it's going to be towards the south. Now, what change do I have to add to nothing to get a vector to the left? Well, I got to add something to the left. And it's that change that the induced flux is going to fight. And so it has to be to the right. Now, to get induced flux to the right, use your thumb. The induced current has to go up the back, down the front, up the back, down the front, up the back, down the front. So it has to go to the right. See if your neighbor is following it. JK, are your neighbors following it? Okay, are you sure? Okay.
Yeah.
Okay.
Yeah.
Now, we found last day that when I left that switch closed, the induced current went away because it's the change that matters, okay? And then we found that when I opened the switch, I got induced current again for just a blink of the eye, but it was in the opposite direction. Let's see if that's the case. With the switch closed, I have external flux over here towards the south pole. When I open that switch, it suddenly goes to zero. Now the change is what I have to add to a vector to the left to turn it into nothing. Well, I've got to add something the opposite direction. Okay. And so this vector to the left plus a vector to the right gives me nothing if they're the same length. Now, it's that purple vector, the change vector, that the induced flux has to fight. So it has to be to the left. And if it's going to the left, induced current is going up the front, down the back, up the front, down the back. And so now the current's going the other way to the left, as we saw last Thursday. Okay. Now, this one is straight out of your tutorial homework. I'm working one of the problems in your tutorial homework, a problem worth 10 points. You are welcome, okay? We have this copper loop, and it's in this, it's a uniform magnetic field, and I'm going to teach you the difference between uniform and constant right now. Uniform is spatial, meaning those field lines are evenly spaced. Everywhere I look, the field is the same strength. But it's not constant in time. It's decreasing in time, which means that even though the field lines stay parallel to each other, they spread out. So I get a weaker and weaker field as time goes on. Now, I'm changing the number of field lines through that loop, am I not? Okay, and so that is going to induce a current. What we want to know is that induced current going to go up the front of the loop or come down the front of the loop? Tell your neighbor. You're going to go up the front of the loop or down the front of the loop?
The B field, that's that way. It's going-
Okay. Folks, I don't usually try to tell you how to live your life, but this time I'm going to. I find that the people who try to just take a shortcut on these problems typically get it wrong. Write out your reasoning, okay? This is how I would reason this if I were taking the exam, okay? I would say, well, what's my external flux at the beginning of the problem, okay? Well, I got a lot of field lines going through the loop to the right. So my flux would be represented by a large vector to the right. And then I would ask myself, what does the external flux look like later? Well, if the field's getting weaker, fewer field lines are going through to the right. They're still going through to the right, okay? Now, what I care about is the change. What do I have to add to that vector to turn it into that vector? I have to add this, and there's the plus sign right there, if you'll forgive me, okay? I stack the head of this vector to the tail of that vector, and what I get is the short vector. It's this change that the induced flux has to fight. If this is to the left, the induced flux has to be to the right, and if it's to the right, use your right thumb, the current's going to go up the back and down the front. Down the front. Okay. Now, let's talk about smart lights. When I moved to Bozeman 33 years ago, there were only a handful of lights in the whole town. I mean, it was just, we were in the sticks, okay? And I remember, everyone that lives there remembers, when we got our first smart light. It was so exciting. It's so exciting. Now, if you're coming home, say from a date or something like that, and it's 3 a.m, and you get to a regular light, you know, it doesn't know you're there, and it stays red, and you have to wait for it. But if you get to a smart light, it knows you're there, it knows you're tired, and it changes the light to green. And if you look down at the pavement at a smart light, you'll find that they've cut a square, a rectangle in the pavement, and they've put something down there and then patched it up. What do they put in the pavement? Tell your neighbor, what do they put down there? Okay. It's just a coil of wire. It's just a coil of wire. Now, it turns out that in Bozeman, the magnetic field of the Earth, because we're so close to Oh, Canada. The magnetic field lines of the earth are coming down into the earth, towards the earth at about 70 degrees, okay? And so if there's not a car on top of that loop, I get a few field lines going down through that loop due to the earth's magnetic field. Now, if you're driving any kind of car, a Toyota, Honda, that doesn't matter, you've got an iron engine block that has a net magnetic field aligned with the Earth's magnetic field, okay? And so when you drive over that loop in the pavement, you're changing the number of field lines that go through that loop. So my question to you is, when you drive onto a smart light detector, does the current flow clockwise or counterclockwise as viewed from above? Okay, and so your clicker question is clockwise, counterclockwise, or I don't know. All right.
What's going on?
We don't know which direction.
Okay. That should be enough time. We still have a few more votes. Get them in. There we go. Okay. Whoa, we are nailing this. It is either clockwise or counterclockwise. Good. Okay, let's do it together. I start out with only 5 field lines going down through that loop. And then as the car rolls over, now I've got 55. I went from 5 to 55. Fight that change, quick. Which way are you gonna send field lines to fight that change? Up. Okay, let your thumb be those field lines. What direction is the current flowing to make field lines up? Counterclockwise, counterclockwise. See if your neighbor got that right, okay? See if your neighbor got that right.
Because I was thinking equal opposites. So if there's going down, it has to go up.
Oh, right. What helps me is like putting myself on.
You're still going.
Where they put. One thing I love this saying.
I taught this principle to my students at University of Washington. And at the University of Washington in Seattle, the parking lot's down this big old hill, and to get into the parking lot, there's one of these loops, and it senses your car, and then it opens the gate to let you in. But to get out, there's not a loop. There's you just have to put 4 quarters in there to get out. And if you forget to bring 4 quarters with you, you've got to march up the mountain again to go change some dollar bill, and it's a pain. So anyway, one of my students came back the very next day and said, "Oh, that is so great, Greg, that is so great." What they came up with was a way to get out of that parking lot without paying. They brought with them the steel lid from their trash can. And when they got up to the gate, the loop was on the other side over there. And so they flung the lid like a frisbee, and as it went across the wire loop, the gate opened. And I went home and I told my wife this was so exciting to me, and I got a lecture about that's wrong, Greg. You taught them bad things. I taught them physics. Bad physics. Okay. Don't do that. Oh, now I taught you. Okay. What I have here is a soft iron coil that has wire wrapped around and around and around it. And when I push this lever here, it's a magnet. You hear that? Magnet, not a magnet. Magnet, not a magnet. Magnet, not a magnet. You're seeing the pattern there. Okay, if I take this ring here and put it like that. Yeah, okay. Now, if I take a plastic ring, yeah, nothing. But what if I take a conducting ring, but it's got a slice in it? Yeah, again, nothing. Now, something that is a little subtle is by changing the magnetic field through these loops, I generated by Faraday's law the exact same EMF voltage around this plastic loop as I did around this conducting loop. The difference is in V equals IR, okay? I got the same V through Faraday's law, but because the R here was huge, I didn't get any current. I didn't turn it into an electromagnet, okay? Whereas here, I've got a small resistance, and so I got a bigger current. When this, let's say that when I hit this button, I send magnetic field lines up through this soft iron. Well, this ring doesn't want to change. It fights change, okay? And the field lines due to this are going to go out and spread. If it started with no field lines and it doesn't like change, where would it go to fight that change? Up there, where the field lines are far apart, okay? Now, if I do the Lenz's law, by suddenly adding a lot of field lines up, by making this a north pole, I change the field lines through the loop, and I fight that change by sending induced flux down. And so it would be a north pole against the north pole, and it hops. Now, if I were to make that colder, okay, if I were to cool that down, I would make it easier for current to flow. That would mean that I would get a bigger current, which would mean that it would become a stronger bar magnet. Okay. Now, when you put something in liquid nitrogen, it boils. You tell them what's going on there? It's boiling, okay? Because this stuff boils at 320 degrees below zero. Everything in the room is 400 degrees Fahrenheit warmer than it wants to boil at. So it boils. But when it stops boiling, that means the ring is the same temperature as the liquid nitrogen. Now, how am I going to get that liquid nitrogen out of there? I didn't think this through very well. I don't want to put anything in there besides my hand. Okay. Okay. Now, first of all, why can I put my hand in there? Because I'm the teacher. Yes. And I'm not very bright. Okay. Now, are we ready? Oh, that light's gonna get hit. Okay. I have a catcher back there. No, you know, I haven't done it with this particular device before, so I don't know how fast it's going to hit you in the forehead. So I'm not going to do that. Now, we want to get to this wonderful levitation track. So let's talk about what we need to understand to get there. You remember that when we were moving this bar across the rails, we had to keep pushing on it. And that's because there were two motions of the charge carriers in the magnetic field. They're moving with the bar this way, and that causes the current. But once the current gets started, that's a magnetic, a motion in a magnetic field that fights the motion. Okay, so this energy that shows up and lights the bulb has to be paid for by the work done by the hand. Okay, now we find that if we take a if we take something, let's just leave that there, okay? If we take something that swings between the poles of a horseshoe magnet, it quickly stops, okay? Because of this induced current, if I just think of this piece of metal as a whole bunch of copper loops, okay? And I'm gonna look at this particular loop there. By swinging into the magnetic field between the two poles of that horseshoe magnet, I'm changing the number of field lines through this loop. I'm adding field lines away from you. Well, that's going to induce current that will send field lines the other way to fight the change. It's going to go counterclockwise around that loop. But I care about it right there. Right there, it's going like that. And current that's going like that in a magnetic field that's going like that is going to give me this magnetic force to fight the motion, to slow it down, so that I have to pay for the energy that shows up. Now, if I take one of those pendulums that has about a bunch of slits in it, so that I can't get a current loop going, you see that, well, it just goes back and forth, 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 back and forth. Okay, but if I just have a loop, it very quickly stops. And if I were to cool this loop down, it would stop even faster. Now, Clark went out of his way to provide this great big chunk of copper here. And indeed, it used to be, let's put those in there. It used to be one huge piece of copper, but yesterday, with Jeremy's help, he made it into two pieces. And what we're going to do with that okay, that was too much. I have here a Mondo magnet, and it's got magnetic field lines that come out of the north and wrap around into the south. Now, copper is a good conductor, and so I can think of this as a whole bunch of conducting loops, and they don't want any change in the number of field lines to them, and so they fight the change. And the more conductive they are, the more they fight, okay? And so when I try to bring this close, I feel that it's fighting my motion. But when it gets colder, it fights it a lot more. I'm trying to smack that copper and it just bounces. I never get close to the copper. And if I spin it to give it some stability, it kind of floats there. Now, if I could get that to be perfectly conducting, not only would it fight the change in the number of field lines, it would win, okay? And it would not allow the field lines to change. And that's what I'm doing with this little puck here. This puck has a thin layer of a superconducting material that becomes superconducting, zero resistance, when it gets at liquid nitrogen temperatures. And I have here strong magnets. And if I take that puck and lock it in place, it doesn't want any change in the number of field lines that go through the puck, through the superconductor. And so it locks those field lines in place. Now, here I've got a magnet, a very strong magnet, that has circular symmetry. So if I lock this in place on that, I can rotate that without changing the number of field lines through the loop, okay? Now, on this track, I just have magnets all the way around that are all identical. And so this thing will have the same number of field lines through it, whether it's here or whether it's there or whether it's there. And so what I find is that, okay, now, whoops. There we go. Now, I can even lock it underneath. That's pretty cool. Now, folks, I would invite you to come up and play with this, but I would encourage you to be careful. These pucks are very, very brittle, and if they hit something hard, they can break, and they're very, very expensive. The kit cost us around $7,000, and one of the most important expensive parts is the pucks. So because we have a wonderful devotional today, and because you want to play with this, why don't we call that the end of the lecture? Thank you, Oliver.